Welcome to the second video in our series on computational electromagnetics theory. In this video, we're going to dive into the fascinating topic of electromagnetic radiation, a cornerstone of modern physics and engineering. Electromagnetic radiation is all around us, from the light we see to the radio waves that power communication systems. It's the mechanism by which energy is transferred through space via oscillating electric and magnetic fields. Understanding how these waves are generated, propagate, and interact with matter is essential for anyone working in fields like telecommunications, radar, and even medical imaging. Throughout this video, we'll explore the fundamental principles governing electromagnetic radiation, beginning with how electromagnetic waves are generated and evolve as they travel through space. We'll also discuss the foundational theories and principles that explain the behavior of these waves, including waveforms like sinusoidal and standing waves, and how they are described by Maxwell's equations. By the end of this session, you'll have a deeper understanding of the nature of electromagnetic radiation and how it applies to real-world technologies. So, let's get started and explore the fascinating world of electromagnetic radiation. On the left side of the slide, you can see an animation of a dipole generating electromagnetic waves, illustrating how an oscillating dipole produces time-varying electric E and magnetic B fields. These fields are governed by Maxwell's equations, which are also depicted next to the dipole. As the charges in the dipole oscillate, the resulting time-varying E and B fields interact and propagate outward, forming electromagnetic waves. To understand how these fields evolve into traveling waves, let's look at the right side of the slide, which breaks down this process over time. T equals 0. Initially, the dipole starts oscillating, generating the first E and B fields. At this moment, the fields are primarily concentrated near the dipole, with complex interactions beginning to emerge. Time equals 0.25 to time equals 0.5. As time progresses, the fields begin to propagate away from the dipole. They are still relatively close to the source, with the wavefronts not yet fully formed, showing complex patterns typical of the Fresnel region, near field, where the fields are strong and highly interactive. Time equals 0/75 to time equals t. By the time we reach time equals t, the fields have transitioned into a well-defined traveling electromagnetic wave, moving away from the source. This is characteristic of the Fraunhofer region, far field, where the wavefronts are planar and the fields are less complex, having evolved into a stable propagating wave. This slide illustrates the entire process, from the initial creation of E and B fields at the dipole to their evolution into traveling electromagnetic waves. Understanding this time evolution is crucial for grasping how electromagnetic waves propagate in free space, and how they transition from complex near-field interactions to the simpler far-field radiation patterns. As we continue to delve into the fundamentals of electromagnetic wave propagation, let's first focus on the left side of the slide, where we have the Poynting theorem in its integral form. This theorem is crucial as it mathematically expresses the conservation of electromagnetic energy within a given system. The integral form of the Poynting theorem is shown here, which relates the rate of energy transfer through a surface to the electromagnetic fields within a volume. In this equation, S is the Poynting vector, E is the electric field, and J is the current density. This integral formulation emphasizes that the Poynting vector S equals E cross dot H isn't just a theoretical construct, but a tangible measure of how electromagnetic energy moves through space. By integrating over a surface, we can determine the total power passing through that surface, and by considering the volume, we can understand how energy is distributed and conserved within that region. On the right side of the slide, we delve into the radiation zones and wavefronts, key concepts that further describe the behavior of these electromagnetic waves as they propagate. In the near-field Fresnel zone, which is close to the source, the wavefronts are spherical, illustrating the complex interaction of electric and magnetic fields that are tightly bound to the source. The Poynting vector in this region can be highly variable, reflecting the intricate energy distribution and the reactive nature of the fields. As we move into the far-field, Fraunhofer zone, the wavefronts straighten out and become planar. Here, the Poynting vector indicates a more uniform and stable flow of energy, aligned with the direction of wave propagation. This is where the waves have transitioned into a simpler form, making it easier to analyze their long-distance behavior. By understanding the Poynting theorem and its integral form, alongside the characteristics of wavefronts and radiation zones, we gain a comprehensive picture of how electromagnetic energy is generated, transferred, and conserved as it travels through space. As we continue our exploration of electromagnetic waves, let's delve into the concept of time-harmonic electromagnetic waves and their role as solutions to the source-free Maxwell's equations. These equations are fundamental in describing how electric and magnetic fields propagate through free space when there are no charges or currents present. Now, on this slide, you can see the source-free Maxwell's equations, which govern the behavior of these fields. When solved under time-harmonic conditions, these equations give rise to the wave equations that describe how these fields oscillate and propagate. Time-harmonic waves are characterized by their sinusoidal variation over time, a key feature that simplifies our understanding of wave phenomena. To help visualize this, we've included a schematic that shows these waves and their relevant parameters. Additionally, we've illustrated the different waveforms that time-harmonic waves can take. First, we have the sinusoidal waveform, which is the most basic and fundamental form. This waveform oscillates smoothly in both time and space, providing a clear and simple picture of wave behavior. Next, we look at standing waves. These are formed by the superposition of two traveling waves of equal amplitude and frequency, moving in opposite directions. The result is a stationary pattern with fixed nodes, where the wave amplitude is 0, and antinodes, where the amplitude is at its maximum. This pattern is particularly significant in resonance systems and cavities, where understanding and controlling wave behavior is crucial. By exploring these waveforms, we gain a deeper understanding of how time-harmonic electromagnetic waves, as solutions to the source-free Maxwell's equations, propagate and interact in free space. This knowledge lays the foundation for further studies and practical applications in electromagnetic theory. Here we continue with aperture radiation, which involves the study of how electromagnetic waves are radiated from an aperture or an opening in a conducting surface. This topic is important for entering the antenna's concept, and other radiating structures emit electromagnetic waves. It connects well with the previous discussions on wave propagation by showing practical applications and real-world implementations of wave theory. As we move into the topic of aperture radiation, we begin by exploring the volume equivalence theorem. This theorem is crucial in understanding how electromagnetic fields can be represented and analyzed using equivalent sources. On this slide, you'll see a series of figures that illustrate the concept. First, in Figure A, we have the generic original problem, which represents the general scenario with a given electromagnetic field distribution. Next, in Figure B, we see the external equivalence, where the original problem is replaced with equivalent sources that produce the same fields outside a certain volume, while Figure C shows the asterisk internal equivalence, where the equivalent sources produce the same fields inside the volume. These equivalent representations simplify complex electromagnetic problems, making them easier to analyze and solve. Moving forward, we introduce Huygens principle, a foundational concept in wave propagation. This principle states that every point on a wavefront can be considered as a source of secondary spherical wavelets, and the new wavefront is formed by the envelope of these wavelets. On the right side of the slide, you'll see an illustration that demonstrates this principle, particularly how a wavefront emerges from an aperture. As the wavefront passes through the aperture, each point within the aperture acts as a secondary source, radiating wavelets that combine to form a new wavefront. This visualization helps us understand how waves propagate and diffract when passing through openings, which is essential in designing and analyzing antennas, lenses, and other electromagnetic systems. By grasping the volume equivalence theorem and Huygens principle, we build a solid foundation for understanding how electromagnetic waves behave when interacting with apertures, paving the way for more advanced topics like antenna theory. As we conclude this section on aperture radiation, we now transition into the core principles of antenna theory, focusing on two foundational concepts. First, let's delve into Lorentz reciprocity. This principle is the cornerstone of how antennas both transmit and receive electromagnetic waves using the same underlying mechanism. Lorentz reciprocity asserts that the electromagnetic response of a system remains consistent, whether we switch the source and observation points. This symmetry is not just a theoretical insight, it's a powerful tool that simplifies the analysis and design of antennas by providing predictable, symmetrical relationships between transmission and reception. This makes it easier to optimize antenna performance in a wide range of practical applications. Next, we explore the Babinet principle, which plays a crucial role in understanding diffraction and how electromagnetic waves interact with apertures and obstacles. The Babinet principle tells us that the diffraction pattern of an aperture is complementary to that of an obstacle with the same shape and size. This principle is essential for analyzing and predicting wave behavior in various scenarios, especially in complex environments where waves encounter obstacles or apertures. By mastering these principles, Lorentz reciprocity and the Babinet principle, we deepen our understanding of antenna operation and electromagnetic wave behavior, enabling us to design more effective communication systems and other electromagnetic applications. In the next video, we will shift our focus to electromagnetic wave propagation and its interaction with materials, exploring how waves behave as they travel through different media and the implications this has for various technologies.